What is life? That's a deep question, obviously, but let's start with a video of a hummingbird. What I'd like to do right now is for you to watch this video. The video itself is an advertisement for a particular brand of slow motion camera, but it will suffice to bolster our discussion to come. You can find many of these on the internet, but let's take a moment to look just at this one. We'll come back after we've watched it. So what are we seeing here, and what does it have to do with the thermodynamics of life? We could mention a number of things, most of them that don't get us to the nub of the matter. We could say, for example, that the hummingbird is hovering, but what does that really tell us? That it's hovering is self-evident. We know this already. We could say that the hummingbird is flapping its wings in a certain pattern to enable it to hover. Again, what does this tell us that's relevant to the thermodynamics of life? What you're seeing here, rather, is an illustration of the fundamental nature of the thermodynamics of life. Let's explore this. Here's a tree with a beautiful flower on the end of the branch and the hummingbird hovering there. If the hummingbird is hovering in place, we can say some things right off. For example, there are at least two forces operating on the hummingbird's body to hold it in place, suspended in the air. To make it hover, in other words. The first is the continual downward force of gravity. We can quantify that force quite precisely. The downward force of gravity is the product of the hummingbird's mass, m, and the gravitational acceleration, g, which is 9.8 meters per second squared. If the average mass of a hummingbird is about 3 grams, or 0.003 kilograms, this means that gravity is pulling down on the hummingbird's body with a force of 9.8 times 0.003, or roughly 29.4 millinewtons. This, by the way, is the hummingbird's weight, which is different from its mass. Despite this downward force, the hummingbird isn't falling down to the ground. It is staying in place, hovering at the flower. This is only possible if there is an equal and opposite force acting upward on the hummingbird's body that is opposing the downward pull of gravity. This force comes about through the hummingbird using its wings to impart downward momentum to the air. We'll get into the details of how this works when we talk about fluids later in the course. Suffice it to say that if the hummingbird is hovering in place, we know that this upward force is also 29.4 millinewtons, but directed upwardly. We recall now that force is a vector quantity, that is, it not only has magnitude, but direction as well. This lets us write a balance of forces equation, which sums the two. Because the force of gravity is equal in magnitude but opposite in direction to the force imparted to the body by the wings, we can say that the balance of forces acting on the hummingbird is a net zero. In terms of Newton's laws of motion, this is why the hummingbird hovers in place. The net forces acting to move the body are exactly balanced against one another, with no motion being the result. But it's not quite so simple. Imagine that same tree, but now with a hummingbird sitting on a branch of the tree 8 meters above the ground. The same balance of forces applies. The hummingbird exerts a force equal to its weight on the branch. The branch, for its part, imparts a force that is equal in magnitude but opposite in direction to the hummingbird's weight. As was the case for the hovering hummingbird, the same balance of forces applies. The bird stays in place, but now the bird just sits there. Unlike when it was hovering, the hummingbird sitting on the branch doesn't need to expend any effort to be motionless. Here's another scenario. Imagine now the hummingbird is sitting on the ground. Again, the hummingbird stays in place because it is held there by a balance of forces. The hummingbird's weight pushes down on the ground with a force equal in magnitude but opposite in direction to the force exerted on the hummingbird by the ground. Clearly, the two states, the hummingbird sitting on the branch and the hummingbird sitting on the ground, are not the same. The hummingbird sitting in the tree is higher off the ground by height h than the hummingbird sitting on the ground, where h is 0. If the hummingbird sitting on the branch fell off, the hummingbird would fall down to the ground. Work would be done on the hummingbird's body by gravity. There's something else to note. The opposite motion does not happen. A hummingbird sitting on the ground does not spontaneously rise up to the branch. The only way the hummingbird gets up from the ground onto the branch is to actively fly up, that is, to do work. We'll come back to this momentarily. Before we go on, though, we need to first lay out some basic principles. These are simply derived from Newton's laws of motion. We've already defined force as the product of something's mass times its acceleration. In SI units, the force is expressed in units of newtons. The hummingbird's weight is expressed in newtons, roughly 30 millinewtons to be precise. Work is the product of force times distance moved. In SI units, work is expressed in joules. Work is also a form of energy. If our hummingbird falls some distance h out of its tree, gravity has done work on the hummingbird's body, and thanks to this formula, we can quantify that quite precisely. If the hummingbird falls out of the tree at a certain velocity, work is being done on the hummingbird at a certain rate. We can therefore define a quantity called power, which is the product of force times velocity, or force times distance divided by time. In SI units, power is expressed in watts. Okay, let's return to our hummingbird, hovering at some height h above the ground. If the hummingbird suddenly stopped hovering, gravity would draw it down to the ground. Physically, gravity would do work on the hummingbird's body, which is simply the product of the force multiplied by the hummingbird's height. If the hummingbird is hovering, gravity becomes potential work, or potential energy, identical in magnitude to the work that would be done if the hummingbird was drawn down to the ground by gravity. To sustain the hummingbird at height h, therefore, work must be done in the opposite direction, at a magnitude and direction opposite to that which could be done by gravity. We can do the same thing as we did with forces. There's an energy balance that is simply the sum of the two quantities of energy. When the hummingbird is hovering, these two forms of energy balance to zero. So, for example, if the hummingbird is hovering at a height of 2 meters, the potential energy is 2 times the hummingbird's weight, or about 58.8 millijoules. The work that must be done by the hummingbird to keep gravity from doing work on its body is also 58.8 millijoules. But, of course, we cannot stop there. Gravity is a force that operates continually, and this means that the hummingbird must do work continually when it hovers. In other words, a hovering hummingbird is really a balance of work rates, that is, a balance of powers. The point of all this is to illustrate 3 different states of the hummingbird. If we look at the hummingbird sitting on the ground, the hummingbird is at equilibrium. There's a balance of forces that keeps that bird in place, but the bird is at a position where its potential energy is 0. Why can we say this? Because the height of the bird above the ground is 0. The hummingbird sitting on the branch is in a state of disequilibrium. It is at disequilibrium because gravity and its height off the ground has imparted to the bird potential energy, which is to say that it is sitting at some height h above the ground. But the hummingbird doesn't move because it's held in place by the balance of forces between the hummingbird and the branch. No more work is needed to hold the hummingbird there than is needed for the hummingbird to be sitting on the ground. We say, therefore, that the hummingbird sitting on the branch is at a state of static disequilibrium. The hovering hummingbird, on the other hand, must do work continually to offset the ability of gravity to do work on the hummingbird's body, that is, to make it fall to the ground. The hummingbird's body is as stationary as the body of the bird sitting on the branch, that is, the hovering hummingbird is also in a state of disequilibrium, but now work must be done continually to sustain the disequilibrium. We say in this case that the hummingbird is in a state of dynamic disequilibrium. Furthermore, because the hummingbird is stationary, the disequilibrium persists as long as the hummingbird is doing work to offset gravity. The hovering hummingbird is therefore at a state of persistent dynamic disequilibrium. When it comes to the thermodynamics of life, this notion of a persistent dynamic disequilibrium is crucial because that is what life is. It's a disequilibrium state that can only be sustained by a continual expenditure of work. If that work ceases, life slides out of its disequilibrium state to equilibrium, or death. Remember this phrase well. Equilibrium is death.